Hello, folks. So we're back to do some more work with Sudoku in Differential Dataflow. And what I've done, I'm on a different computer now. I'm on my desktop, which should go a little bit faster, but unfortunately, I'm backlit, so you don't get to see me. But that's fine. What we have over here is the code as it existed at the end of the last episode. And what I thought we'd do is just go through a little bit of tidying mostly. There's a few things that I'd like to change just to make it be a bit more pleasant. We're just going to try to play around a little bit with incrementally changing the inputs. So showing you like as we go and maybe remove some constraints. The solution, the problem we have at the moment is constrained enough that we find the exact solution just by going and applying some fairly standard rules. As we start to remove some of the input characters, though, what happens is the problem probably gets harder, but how does it change? And so I thought we would make the changes to see that as well, and then maybe also I got some things to tidy up in the main Sudoku logic over here. Nothing, not changing the semantics or anything like that, but just making things a bit more idiomatic. And I thought I'd talk through those so that we could collectively understand what I don't know, like it's thinking out loud about some of the things that we can do with this program. So to refresh everyone's selves, this is currently checked into a work in progress repository that I have on GitHub. You can go grab it if you want. If we run it, this is a debug build at the moment. What it produces is for every of the 81 sort of 9x9 Sudoku locations, it's going to tell us this is over here on the right. It's going to tell us what the initial count was, and after executing the list of possible values that could be there. And what we can sort of notice at the moment is that everything has exactly one value that could possibly be there. Even though some of the folks started with 9 possible values, just one that they can end up with at the end. We confirm that this was actually the intended solution for this particular problem instance. We got all this stuff from SQLite's with recursive documentation page where they have a problem and they tell us what the answer is, and that it takes them 300 milliseconds. They use a different algorithm. So right. Just to recap, while I tidy up some things here, I wanted to walk through what the program looks like. The program has these two parts: a main method over here and a helper method, a Sudoku method. Let's do the Sudoku helper method first. This takes a differential dataflow collection of candidate value row column triples. So each of these mean that this value could still appear at a certain row and a certain column. This is a thing where if someone's told us what the value is as part of the input, there's only one value that can appear at those row and column coordinates. And if someone hasn't told us what can be there, we can start with all 9 possible values. And the method is meant to apply some reasoning, and we'll talk through that, but produce a new collection, a restricted collection of probably fewer possible val row column triples, having applied these Sudoku reasoning rules. And the way that it worked is really not so complicated, I say. We're going to iteratively develop this collection starting from these starting possibilities. Repeatedly, we're going to take this current inner sort of iterate, and we try to figure out which of these locations are actually determined. Meaning there's only one value that could possibly exist at those row and column coordinates. And you can sort of see that we do that by transforming our triples into pairs of row col and val, and then applying the reduce operator that groups together all the values. And if there's only one of them, we're delighted. We produce that as an output. If there's more than one of them, we don't produce anything. Each of these determined locations then exclude based on the 3 rules. Basically, if a value is written down in a location, then that value cannot appear anywhere else in the row, in the column, or in the 3x3 grid cell. So these are all excluded values, and we put them all together in a pile, distinct them up, and then use anti-join to restrict our current candidates, basically to throw away any candidates that are in this list of exclusions. And we repeat. We just sort of keep doing that until for example, we might start with just a few determined locations, but that will, and a whole bunch of folks who have 9 possible values. And after one round of this, those 9 will probably go down, right? Because each of those determined values starts crossing out other locations. And what we're hoping will happen is that some of the locations then become determined, right? So we get some new things that are actual determined locations, because that will actually cause the process of repeated crossing out of candidates to continue, to cascade, hopefully, until there's only one possible value at each location, which would, we would then have solved the problem. Anyhow, that's what this method does. We're going to tidy it up a little bit and replace some more complicated logic with some simpler logic. But also, the place actually I sort of wanted to start with was back in the main method, where we define a timely data flow computation that can run on multiple workers. We have this problem text where it's just 81 characters long, and a dot represents unknown, like a cell that doesn't have anything written down about it. And we're going to correct some comments as we go. We're just going to define the Sudoku data flow and return a handle to the start state. We've got a data flow. The time type that we're currently using is the empty type, because we're not actually, when we wrote the program, we weren't planning on changing the input at the time. Let's change that right now, though, because we're going to want to think about how might we go and change the problem. And then there's a little bit of data flow here. Some of it is a little complicated. Actually, I'm going to tidy up a whole bunch of this, because this stuff that's printing out the state at the end is great, but I don't think we want to, or we're going to do some other stuff, basically. So what I'd like to do, actually, is something different, which summarizes this information for us and just tells us, instead of what every possible value is at every possible location, we're just going to count for each cell the number of possible values that we have there, and then for each of those 9 numbers of possible values, we're going to get a report of how many cells have those values. So let's do that. So I think this is going to be a result. And then we're going to take this and hit it with a map. So this is val row call triple, and really we just want the row in the column. Why do we just want the row in the column? We believe, unless something has gone wrong, that each value is only proposed once, and all that we're really interested in is knowing how many times is each row and column proposed. So if there's only one value, we'll only see row column once. If there's 3 values, we'll see it 3 times. The actual value isn't so interesting to us. So we're going to then count this. Count is this differential data flow operator that takes a collection of any type and returns pairs of that type and an integer, which is how many times did it occur. Then we're going to say, actually, to be honest, we don't really care about the row and the column. We really just care about the number of times that this showed up. So we're just going to keep that. And depending on what we want to see, we could go and count again to see how many times. So these are the numbers 1 through 9, we believe, unless some logic has gone wrong. But what I think we can just do is call the consolidate function. And what consolidate does is just takes lots of changes that might have occurred for different reasons. So this, the number 5 might show up from a few different rows and columns. Consolidate will take all those occurrences of the number 5, put them together, and tell us what the count is there. And I think we can just do an inspect now and get out something worth looking at least. Yeah, so this is, unless there's some typos or something like that, this is going to tell us about the final counts. And hopefully what we'll see here is the number 1, 81 times. That would be appropriate, or that would confirm that we we believe we found one unique solution for all of this. And let's see if that actually works. While it's building, I think this should build relatively quickly. But while that's building, let me sketch the next thing we want to do. We've currently hardwired our. Oops. Okay, so that ran. Great. And indeed, we have the value 1 times 0, 81 times. Good news. So the next thing we're going to try to do, just to make this a bit more interesting to look at, is think about changing the inputs a little bit. So think about, instead of just having the static problem, maybe the static problem, then we start removing some of the values. Maybe we get rid of this 5, then we get rid of the 3, maybe the 7 if we're really excited. We can't really do that at the moment because we have this imperative way that we drive around the ingestion. I don't want to have to do all that nonsense. So what I think we might actually do is change the data flow ever so slightly so that start, instead of containing the actual values, rows, and columns, it's going to contain the instructions for what to do with them. So it's going to just contain bytes as before, but instead of the values 1 up through 9, we're going to just put in whatever the instruction was. So that's going to be val row call. And this logic, which is super useful, will get put into the data flow so that we can modify these symbols that we put in and then let their changes sort of get correctly updated as well. So if we do like let board be start.flatmap, and there's still this val row call coming in, but they're just these bytes that one of them might be a period. Flatmap, we want flatmap because each of these things might produce either, for sure, either 1 entry or 9 possibly coming out. And flatmap wants us to return an iterator over our output type. Our output type is going to be triples again of U8s, val row column triples. Unfortunately, it has to be 1 iterator that comes back. And we have this if where we sort of want to do 2 different types of things. So we're going to be a bit sloppy and just put both of these into a vector. So even though both of these we can sort of statically know how big they should be, they don't really need an allocation. We're just going to do it anyhow because it makes our lives easy. And I think if we do that roughly, things look possibly good. Let's see what happens. Oops. Yeah, we need our semicolons for sure. Oh, we definitely screwed up. We should do board down there. Seems good. So what this will let us do is more easily write some changes, basically. We could imagine going and stripping some things out. We could, for example, walk through this whole board in order and remove each of these clues, which at the end will get us back into a world where there are 9 possible values for every single location. That's the end. That sounds interesting. Should we do that? Let's try it. So we are going to write some code. This is essentially the same thing. We're going to walk through these bytes again. So we're going to do for count. Yeah, I guess count, comma, val. Sorry, I'm literally just going to copy the exact same thing. Except rather than inserting a thing, we're going to do a little bit more logic. So down here, we want to change the time at which these changes that we're about to make occur. So we don't want to do them all at once. We could all at once remove all of these hints, but I think for this to be interesting, I actually want to slowly walk them back out so that we can see them change round by round. So I think what we want to do is start dot advance 2, and I'm going to do count is here, let's do index. Why count is even. Oh, okay. Well, I'm not sure why we use count as a variable, but index, I'm gonna say +1, meaning we'll start this. This is at time 0. We're gonna go to time 1 now. Do some stuff at time 1, and at the end of all the stuff, we will sort of spin the worker for a little while and make sure that it updates the computation correctly. So we need to advance the time. We need to call flush. These are two separate things. This advances a logical timestamp internal to differential data flow, and this moves that information down to the timely data flow system. This is pretty lightweight to do. So we could do 100 of these at a time, and it's really quite cheap. This actually prompts some work in timely data flow and isn't massively expensive, but it's if we wanted to do this once per record, advancing the time, we can. We don't really want to do this once per record in timely data flow. So we are going to do the following. We're going to remove the value, and we're going to insert a different value, which is going to be let's just do great. So this is a change that will undo what we'd previously done and change it to a dot. This should be a no-op for anything that was already a dot, so that's fine. And for anything else, we're just sort of deleting that constraint, which, yeah, a bit weird. All right. I kind of want to write this a little differently, actually. So idiomatically, like a thing that's relatively easy to do is like do some changes, then change. Run the worker, basically, like advance the inputs, run the worker, having made the changes. I guess we don't necessarily have to. I'm trying to write this in a way where each of these loop steps is sort of the same, make some changes to the data, advance the input, run the worker, which I'm going to try to do anyhow, though I think we end up with slightly awkward loop indexes and stuff like that. So we don't want this to occur at, I guess what we can do is we can always just do let round equals so we can just pull the round out there. Flush. And now we don't even need to look at the don't even need to iterate, do the enumerate there to look at the count. And now we do something along the lines of while we have this probe, so like while probe less than start.time worker.step. And what this will do is this will count up basically to the next legit round. So it starts at 0. We do a bunch of stuff at 0. We should probably do something very analogous to this right up here. So we can advance to 1 because it was at 0. Flush things, run the worker, and let's we have a timer lying around. Let's print out some timer thing. This will tell us roughly how much work got done, how much work got done, but like how long did we take? So round is complete. Not round plus 1, just round is complete here. This act doesn't actually move us into round plus 1. It closes out round and allows the system to start working on round, and it leaves round plus 1 open and available to be worked on. Let's see what goes on here. Okay, we got a bunch of we need semicolons. That's exciting. Expected value found module. hopefully that's just a semicolon issue. Yeah, this makes sense. Dot elapsed, need to actually supply all the arguments. Good value. Oh, right, sorry. We totally need this count thing because that drove our row column thing. Great. Cool. All right. Now, this will run. This is a debug build. I don't think this should be a catastrophic amount of time between these updates. Yeah, cool. So you can see a bunch of changes here. You can see up to 81. Does that make sense? Yes, good. Sorry. We will also see a 0. So there's 82 lines printed. And yeah, they're revealing how these changes have unrolled. So for example, at the end of round 0, so a thing that I should probably fix this. We don't actually have the probe on the other end of the inspect, which has meant that there's a little bit of a race between printing this bit of data flow here and printing our round complete stuff. So with the probe put after the inspect, that should prevent us from announcing that the round is complete until these counts have actually been printed, and that's the same thing to do if you want to keep track of what's actually going on in your computer. So we have final counts, 81 occurrences of 1 at the end of round 0. Round 1, where we delete the 5, nothing changes. Apparently that stays the same. Then we delete, it looks like, the 3 here, and that changes some stuff. Pretty exciting. Next 2 rounds don't do anything, which sort of makes sense because they were dots, right? So nothing actually changed. We change a bunch of stuff now with that 7 going away. And then 4 rounds of nothing changing. I guess that corresponds to these 4 dots. It's quite possible, like we do potentially kind of expect that every round will change a thing, because if nothing else, we're removing one very well-defined value, right? So it's a little surprising, actually, possibly, that when we removed this 5, that didn't cause anything to be any less well-defined. That means we're able to rederive that this should be a 5. Couldn't be anything else, right? We know it can be a 5, and apparently it couldn't be anything else. So it's sort of interesting that we didn't lose track of the fact that it could be a 5. But as you can see, I'm guessing that a lot of the times when we remove a character, we actually do see a change in the output result. Though these changes, you can do the reasoning in your head if you want. These changes are going to be monotonic. Like as we remove these hints, we only learn less about the board until ultimately we arrive in a world where it's all 9s. In the very last round, we got 21 more 9s, which I suppose, like when we remove the last, we remove this final character, there were a bunch of things that it crossed out, right? There were 8 other rows, 8 other columns, and a bunch of people in the same cell. And I guess what it worked out to was, well, anyhow, I'm going to believe that the math is correct, but I'm not going to try to do it live. Sort of curious to see if we run this in release mode, how long does it take? So it took, looks like, almost a second to do all of these updates. It's not obvious that a second is not a great time to be solving Sudoku problems like this in. This computer does, well, we'll see. So this is, okay. So apparently we can do the whole thing in 45 milliseconds. And if we go and we look up a little bit here, first round, then sort of 5 milliseconds, and these updates take, looks like single-digit milliseconds to update, and we pull off 80-ish of them in the limit in about 40 additional milliseconds. So we're not super concerned about performance here. I'm going to be doing some tweaks in just a moment that are going to try to make some of the code a bit more idiomatic, though. Use better patterns for data flow processing, and we might improve some of these times a little bit, but these numbers are small enough that I think we're not necessarily going to see a lot of lift from fixing them. So let's talk about that then. What sorts of changes might we want to go and make? And I'm going to look mostly over here in this Sudoku problem method. Right. And there's a few things that leapt to my mind. One of them is that this, the first one obviously is that these are all horribly misformatted, and we want to indent them one so that we can stop being stressed out about that. So this logic here, where we take a collection of candidates and we look at those row and column, look for those rows and columns that have a single value and restrict our attention to just that value. This method is fine. It's not deeply problematic, but it does some things that I think are a little silly. Mostly, this reduce that goes and says, hey, if you've got length 1, let me just report that one value, does a lot of work for rows and columns where there are multiple values. So if you've got 5 or 6 values, let's say you had 6 values and I've just gone down to 5. We're going to go and do all that change logic to figure out, like, oh, what did you used to be? What are you now? What are you? And in each case, we're just conclude, oh, you shouldn't have produced anything. That was a big waste of time. So there's a faster way to do this. Faster, possibly not actually in terms of how long it takes to run, but generally, if what you want to do is restrict your attention to keys of interest and fish out those values, if you can find those keys of interest promptly and then just do something like a join to pull out the relevant keys, that's a great way to do things. So we're going to rewrite stuff that way. So we're going to let determined be, what do we want? We want to take inner, and we want to find rows and columns that occur just once, right? So what we can do is take, we don't really care about the val, so we're going to use similar sort of thing to our reporting up here, where we say, the specific values aren't all that interesting to us, or at least not yet. Let's just take the rows and columns, ignore the val, and we are going to use a cute differential dataflow method called threshold. And what does threshold do? It takes the key, which is the row-column pair, and it also takes the count, so the number of times that this has occurred in the collection. And we can specify, through a closure, any new count we want. In particular, we can say something like, if count is exactly 1, then 1, else 0. So this takes this collection of rows and columns, each some multiple numbers of times, and lets us write some logic that updates as these counts update, changes what we produce as a collection, how many times we produce this key in the output as a function of what the values are. So this, when it occurs 0 times, it occurs 0 times in the output. When it occurs 1 time, it occurs 1 time in the output. And as soon as it goes up to 2 or beyond, it also occurs 0 times in the output. So this should just be those distinct rows and columns that occur exactly once in inner. And the reason this is interesting, this is a bit faster to maintain in the limit. With 9 values, maybe not so much, but in the limit, a bit faster to maintain, because without having to keep track of all the values, we just keep track of the count. So it's sort of one number we keep for each of these rows and columns. And we can now do something like inner.map. So if we do we're going to do a join to pick out the relevant rows and columns. Actually, a semi-join. So what a semi-join does, it's like a join, but what a semi-join does is take key value pairs. So in this case, the key is the row and the column value, and semi-join takes a collection of keys, and it's basically just like a join between them where there's no value associated with the second one. So it takes the multiplicities of each key in here and multiplies these key value pairs by the multiplicity of their key in determined. And that happens to be just 1 or 0. So essentially it's just restricting this collection down to those rows and columns present in this set. Sweet. So this is a different way to produce this determined collection. And I think of it as a bit more idiomatic because we more promptly suppress changes that aren't relevant. We don't redo a lot of work in a reduce for row and column pairs that just don't have anything, that aren't going to contribute anything of interest. Those changes just sort of die right there. So let's squish that out. Hopefully this, let's see if this compiles. Yeah, great. I don't actually expect exciting performance changes here. Hopefully not performance regressions. So we're going to do them anyhow because like these are the sorts of things that you want to do if you're flinging around billions of records. If these are, instead of being possible values 1 through 9, these are are certain user IDs uniquely determined. So like yes, this actually went a little bit slower. Same amount of time to start up, but the elapsed time at the end, I assume this is reproducible. Let's check. Yeah, it's actually a little slower. Bunch of reasons that could be. I'm not going to. These are 2 stateful operators, whereas reduce was 1 stateful operator before. There's a few other optimizations we could do here, but I don't want to bog down the discussion with them. This state that is held in threshold could be threaded into. Here we're sort of maintaining 2 copies of the same collection indexed in memory. Threshold and threshold's output is also maintained by semi-joins input. We could fuse those together and get some of the performance back, but we're not. That's not why we're here. Cool. Okay, so this is. Let me just leave a comment here. If I go to identify the row call pairs with a single candidate value, great. The next pile of work down here roughly is to take those determined locations and use them to exclude other candidates. So these are, it's just, each of them are a mouthful. We're not going to change that really. Flat maps, they take some amount of time, but fundamentally they're not stateful operators. There's these stateless things that as records flow in, as a new record becomes determined, we produce a few more locations that get excluded. It's totally fine. But what we do with those exclusions is we pile them all together, the 3 different ways that data might get excluded, put them back into the form that the iterating collection of candidates have, make them distinct, and then do an anti-join. Anti-join is sort of the opposite of a semi-join. It leaves things behind that don't occur in the second relation, and consolidate. And there's a bunch of stuff going on here. We're going to make this a little bit simpler, and I think also more efficient, or more idiomatic at least. And the way we're going to do that is we don't really need to use all this anti-join complicated stuff. I just told you about threshold. There's a cute way to use threshold here that implements all of this nonsense a little bit more efficiently under some assumptions that I'll try to articulate. So what we're going to do is we're going to take all of our exclusions here that now look like the same shape as inner, and we're just going to negate them, and we're going to concatenate in inner. So this is now inner minus all of these exclusions. Those will be all of those candidates minus, for every val, row, and column, minus the number of ways it could have been excluded. So that is initially 1 for every candidate. It goes to 0 if there's at least 1 exclusion. It might go to negative. That might go -1 or -2, something like that. So what we're just going to do is write a little bit of threshold here, where, again, we don't really care about the row and the column. We're going to use the same logic for each row and column. And if we look at the count, what we really want is if this count, again, it's the exact same thing as above, but for a different reason, is exactly 1, produce 1, else, and the else could be 0, is y, sorry, it could be that it's 0, could be that it's -1, could be -2. In any case, we're just going to make it 0 if it's anything other than exactly 1. And yeah, that's the same logic as all this stuff down here, basically. Threshold and distinct both take, they're both stateful, but they both track roughly the same amount of memory, and then this anti-join is just not necessary anymore. So you can just sort of tidy all that up. Oh yeah, sorry. This is actually just, we're just returning this thing back as the next iterate. And that's, so yeah, we don't even need to bind it to anything. Sort of just running the release builds to try to get a sense for it. Does any of this actually make our lives any better? And you're gonna have to take my word on it that stuff like this is a good idea on bigger data sets. I apologize that it's not actually better in this particular one. All right, so we got a bunch of time back. That's good. This is a little faster now. I'm not entirely sure what the error bars are on these. I suppose let's rerun it and see. Yeah, I guess for some reason there's some annoying non-determinism. But we got some time back in the tail here, and that makes a little sense. There's just a little less state we're maintaining, and consequently a little less work that we're doing. Neat. Okay. And there's one other change that is a bit more head scratchy, which is the following. As we iterate this inner collection, we use it a few times, and it's important, obviously, that we use this collection, right? Like as the iteration happens, we're changing the collection. We should behave differently as that collection changes. Particularly when we determine, right, like which row and column pairs have a single candidate value, we absolutely need to be using inner to go and figure that out. Similarly, when we pick out the values at those locations, absolutely want to be using the current value of inner here. Turns out we don't actually need the current value of inner down here. And I'm going to try to explain why that is, and also why that might be a good idea to swap it out for something else. So what we're looking at down here is we've already computed from all of the determined values all of the exclusions that we possibly can produce. And then we're going to subtract those off of, in this case, our current candidates, but we could totally have just used the initial candidates that came in, these start candidates up here. So we could totally say start.enter of inner.scope. And that says, take this outer collection, start, bring it into this iterative scope as a static collection, essentially. One that, sorry, not static, but like one that does not change as the iteration happens. It's still a collection that can change as we add and remove things to it. But essentially within the scope, it's going to be constant. And here, what we're saying is take all of those initial candidates and subtract off everything that's excluded. And that's great. That still does exactly the right thing of, it should produce exactly the same thing as having put inner in there. Because, well, I don't know why because, but yeah, it's still correct. And the reason that it's interesting is that this collection changes less than inner changes. And what do I mean by that? Inner changes in a few different ways. So like inner goes from the initially empty collection up to, in the very first round, something that contains all of the entries of start, followed by, as we iterate, followed by, well, there's various subtractions, basically. As we cross out various candidates, size of inner shrinks a bit, and things go away. As those things go away, when we were using inner in here, inner would say, hey, I just lost some candidates. You better make sure to go and update that threshold thing correctly. Like, I just had a thing that said, I might want to be the number 5 at a particular location, but I'm not that anymore. Hey, make sure to go and change this from a 1 to a 0 before we subtract. It's like, none of that actually matters. We don't need to be doing that. So that work, not only do we not need to be doing it for correctness. That's just work. Like it's changes that have to happen, and we see this a lot in graph computations where there's the base case essentially. So in some sense, this is what we're doing: is we're adding in the base case, and all of this stuff up here is the thing that's actually developing. Sorry, I should have highlighted all of it. The thing is actually developing iteratively. So base case of all the data, and then an iteratively expanding list of exclusions is actually what's growing. So, oops, sorry. So let's see if this actually improve things at all. I'm curious. Often, like in graph processing stuff, this is often super helpful because you have node state, for example, that is initially something, I don't know, like a few locations in the graph that you're starting your query from, and then some node state that evolves, like distances or something like that. And using the evolving distances here, yeah, look, things got faster again, probably. Yeah, cool. So I think that looks, I mean, both times we just ran it, it was a little bit faster, sort of on the like 10% amounts. There's basically just a little less churn in the data flow. And since it's not important churn, like since it's not actually doing something helpful to go and subtract out that data, we don't need it. There might be a world in which it is helpful to go and subtract out that data, like if we're compacting up the state down here or something like that, where we want to reduce the memory footprint by retracting some data, might be good to do. But if we don't need to tell anyone about the retractions, we still get the same answer. It's just busy work. Cool. This is, I think, as far as I want to go in this particular round of talking. I'll commit all of this stuff. We're gonna tidy up and make idiomatic. Cool. Push all that stuff there. Do I really not have this? Yeah, I guess I'll need to do this a bit. I have two-factor authentication set up. I'm not sure why it's asking for passwords and stuff, but great. I'll push it in a little bit off camera. The plan for the next episode, for folks who are excited about this sort of thing, is to look into writing a bit of backtracking. So the actual, like in the hard Sudoku problems, you don't actually solve the whole problem just by these forward inferencing rules where you just cross out candidates that aren't supported. That you can do that, and that's helpful. But you end up in a stable solution to this fixed point computation where there are still locations with multiple values. And like as we saw back up here, like as soon as if we get rid of the 5 and the 3 at the beginning of this problem, these folks over here, we end up in a world where, having done all of the thinking that we can do without any guessing, there are now 6 locations that have 2 possible values. And it might be that that's, the problem is underspecified now, and there are actually just 6 locations that have 2 possible values. But if you've done Sudoku before, invariably what this means is that if you fix one of those 2, that locks down some of the other choices. So in particular, I'm sure this is one of the locations that's underdetermined, and if we choose it to be a 3, that determines everything else, because we know that if the 3 were actually there, everything would be determined. It could be something else, it seems like. And possibly if you fix it to be that other thing, the degrees of freedom go away as well. So the plan is, try to put the logic in that starts doing this type of guessing in a nice and productive way. And I'm not entirely sure. The logic that we've done so far has had the nice problem that when the system is very under-constrained, like down here at the end, that's fine. Like we just, we produce a bunch of information saying, yeah, we don't know. And the backtracking stuff is actually going to go through and probably start to enumerate lots of solutions. And, when we have absolutely no hints at all, that's not 9 to the 81 exactly, but like there's a lot of degrees of freedom, basically. So exactly what we do, we have to be a bit more careful about what do we run this on and stuff like that. But it hopefully it'll be interesting to see that develop. But for now, I'm gonna stop. Try to do a slightly shorter session so that people can make time for other things. But we'll come back with some more stuff about backtracking Sudoku in the future. Thanks.